Hello, Dr. Sven Bone. Thanks for joining us. We're looking here at the Badger screw. You are the inventor, or maybe you had some other smart people co-invent this with you. This is a prosthetic screw going direct to MUA. Tell us about the Badger screw, what it is, the geometry, why you invented the screw, because there's already some decent screws on the market. And so now you're coming saying, hey, I got a better one, or I got a really good one. Talk to us about this screw and why you thought the market needed the Badger screw.
Yeah. I think the whole goal with starting Smart Mouth Technologies is I wanted, I really wanted to bring a lot of engineering rigor into the space. And so we are a hardware and software company, and our mission is to really bring a lot of progress into the industry is in a very rigorous manner. So I've got lots of engineers on staff, and we are really excited to kind of innovate into this space. So there's a lot of industries out there. There's aerospace and there's automotive. We are, and I'm kind of just interested in bringing some of that rigor into kind of our industry with product with hardware and software solutions. So we're just a big pile of nerds, and we're excited to to kind of to work and work through ideas in a systematic way. And
I love
so
it. You're
my background, just to kind of preface that, my
yeah.
background is so I'm a prosthodontist, but before I went into dental school, my undergrad degrees are in physics and mathematics. And so I kind of
Okay.
have, I can live in both spaces. So I, a clinician for sure. And so I can see the problems that manifest themselves in the clinical environment. And then also my background allows me to work with engineers because I'm not an engineer myself, but I understand all the fundamentals so I can have really good conversations with them and kind of help guide us as a team into innovative solutions.
So a prosthodontist, physician,
That's right.
physics expert, and mathematician.
Yeah.
Wow, that's quite the combination. I've never met anyone with that
Yeah.
combination, and that's fascinating. So here, let me play the video here.
Yeah.
Here's the Badger screw in action. Yeah, just tell us about this. What are we looking at?
So this is we got to give credit with credit's due. This is Diego Marquez. He's a prosthodontist, and he works with Nestor Marquez. I think they're brothers. They're I know Nestor from Orca through that's a really wonderful educational opportunity for people to learn about full arch. And this is his brother is nerding out, and this is, I believe, he machined this on an Armin gearbox. So they trying to basically get all their cam and tooling ready to go to manufacture prosthetics direct to MUA with the Badger screw. And so this went up on Instagram, and so it's kind of a fun little, it's like, hey, it's working.
I love this. So the geometry of the Badger screw is a little different. Has some unique
Right.
properties and how it seats into the prosthetic. Maybe talk to us about that, like the seating geometry of the Badger screw and some of the uniqueness of the shape and why you engineered it that way.
Yeah. The in the development, and we started working on the Badger screw about a year and a half, 2 years ago, and we were looking at basically computational models, so finite element analysis models of how can we distribute stress in the prosthesis, in the material. What is the what's an ideal kind of shape to design a screw seat with? And so going through a lot of different designs. This is kind of like how it's done in other industries is you always do computational models first, then you prototype, and then you validate before you go into production. And so this is the design that we kind of developed, and it's a concave kind of profile, and it is designed to basically achieve very high clamping forces and also distribute stress in a very controlled manner through the material and where it's generally at its thickest.
So, what problems were you trying to solve with this geometry? So, like, you invented a screw saying we're going to shape it like this so it behaves in a certain way that
Right.
avoids some of these other challenges with prosthetic screws.
Yeah, so the philosophy should always be designed to performance requirements. So we have performance goals that we want to achieve. So high clamping force, minimizing stress, or controlling stress, and also we also wanted the smallest screw channel on available today on the market because the screw access hole too is an area where stress concentrates. So minimizing that was
Yeah.
also a performance goal that we wanted.
What's the screw access hole diameter that you indicate for the Badger
That's
screw?
just over 2 millimeters. Like it's about like 2.05.
2.05. And is that the narrowest screw channel on the market?
Yeah, I believe so. From what we've seen as far as any direct to MUA screw. So
Wow.
relatively, this kind of gives you an idea across the market that about the major direct to kind of MUA screws. We're definitely the smallest one that we've measured so far. And so what we found is through our basically run we use a 15 millimeter cantilever test, and it's a static load test. So essentially we're putting a force onto about 15 millimeters away from the screw access hole. So you can see this is the rig that we have set up, and we are applying a load right here, and that's about 15 millimeters away, and we're essentially the fulcrum point is here, right? And this is where you're going to see tension.
Of course.
And this is kind of the worst case scenario, right? Screw access hole right in a high stress concentration to begin with where we have embrasure spaces. These are sharp, and I can go through about how complex geometry affects the stresses, the stress tensor in these shapes. And
Yeah, I've
so
heard a rule of thumb of like a tooth and a half cantilever max, or like what's the rule of thumb on a cantilever?
So yeah, so that gets to another really interesting point about our industry is we have rules of thumb, right?
Exactly.
Yeah. But the reason why these rules of thumb exist is because it's incredibly complex. The underlying mechanics of of this is really complicated. But the rule of thumb generally is maximum of 15 millimeters of cantilever and then 1.5 times the AP spread. And
Yeah.
so this is kind of right in line with what you would see in the real world. So
Okay.
this is not like insane tooth and a half kind of thing. These are cantilevers exist out there, and what we have to do is also every patient is different, so every patient is going to put a specific load on their prosthesis. So a little old lady eating mush is going to be totally different than somebody that's like a middle-aged male with bruxism.
So,
And so it's like
totally.
totally different environment, and so rules of thumb fall apart when we actually talk about the real physics that's going on that patient sitting in your chair.
So, little old lady, you might be comfortable giving her that full 15 millimeters, or
Yeah.
maybe a couple more if you wanted to
Yeah.
push the envelope. But then a much stronger, bigger patient with bruxism, you'd need to know, we should probably shorten it a little bit and just take some stress out of the way with our prosthetic design.
Absolutely. So there's, I mean, you can even get violated even more, with a little old lady. I mean, you can get away with more. You want to design to the performance requirements of the system.
Hmm. So what precisely are you testing here with this test? And what are you measuring? What are you testing? What is the discovery you're making with this test here?
So what this does is this is testing what is the braking force, what is the maximum force that this scenario will hold up. And so the controls, it's fairly well controlled. So the distance where the force is being applied, the variable here is the actual prosthetic screw. And so same design, same manufacturing. And so the only thing that changes is the screw hole diameter. So we're testing a bunch of different screws and we're just breaking arches here.
Okay. All variables being controlled except for the screw channel and the screw seat geometry.
Correct. And so, what we're finding is that basically screw hole size matters. And so it takes, and this is in PMMA. We're doing zirconia next week, and we're also doing tie bases too, and we're also doing bars. And so we're because that cantilevers, they are going to occur. We have to manage. We have to deal with their higher risk fundamentally, and so we're kind of working on the engineering of how do we best manage those.
So, I mean, maybe this is too simple of a conclusion here, but if just the screw hole size is the variable you're testing for, then the Badger screw having the smaller screw hole size all by itself, that one element you're saying is the most significant contributor to being stronger, the prosthetic being stronger and more resistant to forces in the mouth.
No, that's just one performance thing that we're testing. We also have the highest clamping force that we've tested so far, and we'll get to that. But just the data that we're collecting and the testing that we're doing, kind of like it's basically fundamental to who we are as a company, and goals are, because we deeply want to understand the kind of the mechanics that we're dealing with in this environment. And so
all things being equal, the size of the screw hole channel itself, how significant then of a contributor to prosthetic strength is that one feature?
It can be a pretty significant contributor. So in this case, this is the difference between having success and failure. So if you have a patient that bites down with 200 newtons of force on this cantilever, they have like an olive pit moment, right?
Yeah.
If they bite down at 200 newtons, this prosthesis would survive, and all of the other ones would fracture and fail.
And it's same material.
Same material, same design.
The only variable we're testing is screw axis, the screw channel.
Yeah. So this is, and then this is just for, PMMA, right? And in zirconia, that data is going to be coming out here pretty soon. So probably within a week or so.
Well, I can't wait to see that. We'll have to do an update.
Yeah, because that really matters too. And zirconia is a totally different material, right?
Yeah, I mean, the milling and then sintering and cooling, and there's a lot of other variables to control to make sure you're handling it properly.
Yeah, absolutely. Zirconia is a miracle that it works. It's honestly, I'm just blown away at how precise it can be, especially when you're looking at these big arches and stuff. And when I see, there's nothing that makes my day more than when I put that first screw in and I see bullseyes all across the entire arch. So I
Uh,
deliver one screw
yeah.
first, and then I look at all the access holes, and I'm looking for bullseyes, right? So I'm trying to detect. That's kind of like a clinical trick for detecting, uh, centering distortion, and it's just blows me away that it actually works.
I know we're oversized milling and
Yeah,
predicting shrinkage to
yeah.
down to the micron. You
I,
know.
I mean, like within like 10, 15, seems like 10, like that error is probably, it's probably more like 25 or somewhere around there. But it's still pretty amazing at how precise it can be.
All right, you've mentioned clamping force a few times, so
Yeah.
let's move on to clamping force. Uh, I'm gonna just reveal some ignorance. What exactly is clamping force? Define that for me, so I make sure I understand it clearly. And then how are you measuring it, and how does your geometry accommodate that better?
You know, let's, I'm wondering if we should just get to, let's talk about like what is, maybe let's talk about screw, like how a screw works. And then we'll kind of get to that. So basically, a screw has been around as and used as a fastener since the Roman times, so over 2,000 years, right?
Yes.
So and a screw is a fastener specifically is a pretty amazing thing. So its whole job, it's very simple. Its whole job is to convert rotational motion into linear motion, right? That's what its job is. And so the forces involved are torque. That's what we know. That's what we think about. And so when you measure, 35, can zoom in a little bit more. But when you measure like, 35 Newton centimeters or 15 Newton centimeters, what does that really mean? And so the total torque has to do with the friction of the screw head and the friction of the screw threads and
Right.
also the preload, which is the stretch of the screw. And
Oh,
so when you're measuring, there's a whole lot of things that go into what that number actually means.
the screw stretches when you torque it.
Correct.
I've actually heard this. After you torque a screw, you shouldn't reuse it if you needed to back it out for whatever reason.
Yeah, so that's not necessarily true. That's if there's been damage. So when you have stretched a screw to the point where it's beyond elastic deformation. So elastic deformation is when you stretch a screw and it bounces back.
Hmm.
Plastic deformation is when you stretch a screw and it doesn't bounce back. So it's permanently deformed. It's permanently elongated. And in that process, micro cracks always occur right at the first threads. This is where the highest amount of concentrates. And so if you overstretch a screw, that's where damage is done. And you can't look at a screw unless you measure it with a micrometer. You can't look at it and say it's been damaged. You should over it.
Yeah, I've put a screw into the wall, a drywall screw, and it doesn't happen often, but you find a stud, you get a lot of torque on it, and then the head pops off.
Yeah.
And that's my guess is because all that stress is concentrated right between the head and those threads.
Yeah, it depends, like on machine screws and in like when it's being clamped down, the I've got some other visuals to show where how that stress is distributed along the screw. But
All
yeah,
right, so torque should be, is there a universal rule of thumb for torque force on a screw, or is it different by screw design?
it's all dependent on screw design.
Okay.
And so if you look at the components, in physics, we break down the problem into its components. Like torque on a torque wrench, well, it's the sum of all of these other contributing factors. And you kind of got to, it's good to know all the little components that go into it. So the biggest one of the biggest components to what that torque means is we are fighting friction. It can be between 40 and 90% of what that torque value means. And so screw head friction consumes or robs us of what we want, which is preload.
Yeah, so the screw head friction could get tighter, or it's giving you a torque value before the threads are actually doing their job, right?
Correct. Because what we want is how the screw interfaces with the material is really important. And thread friction in machine screws like what we're dealing with the M1 1.4 thread pattern, it is very low. It's only like 5 to 10% of that torque. So so really we can kind of throw that one out. It doesn't contribute a lot. It doesn't steal a lot of torque or preload from us. And then preload can vary dramatically, surprisingly a lot. It can vary from you're only getting 10% of that preload from that torque that you're putting on the screw, or it could be higher, like up to 55. But these are generally how to think of it. So screw head design matters, and preload is the goal. And preload, clamping force. So clamping force is the force that we want to maintain the prosthesis on the MUAs and maintain stability. The way I look at it is like an energy model. So it's a store of potential energy. And so we're torquing the screws down, and we're storing, by stretching the screw, we're storing some potential energy to resist the forces that they're exposed to.
Let me repeat this back to make sure I understand, because I think I might. So the screw head has force, and it's wrestling between the screw head and the screw threads. And if that force is as designed, you're good. But if the screw head is absorbing all the force and the threads are not, then you're not getting good preload.
Yeah.
Is that correct?
So the way to look at it is that by doing that rotational motion, like torquing the screw down, if friction is stealing away from stretching the screw,
Friction on the head.
friction
Friction
on
on
the
the
head,
threads.
right? Yeah,
Does it matter where the friction?
friction on the threads is very low. So the threads are what's engaging the, like right in here. So this is the part that's doing the conversion from rotation to linear motion, right? And what is stealing is what we can control is the screw head, and the amount of friction that's involved.
So most of the force is at the screw head,
Yes.
and then just the first couple of threads.
So the preload is forcing this part down and holding it against this platform. So that is the clamping force that's occurring. And preload is clamping force, and that is that store of potential energy to resist. Because if we didn't have a screw there, the prosthesis would fly off. And so preload is the only thing that's keeping that prosthesis anchored to that platform.
Now, is this related, everything we just discussed here, related to screw loosening?
It is, because screw loosening occurs when you lose preload. So over time, cyclic loading, chewing.
I mean, vibration, how does vibration not loosen every screw in the mouth, right?
It does. The universe wants screws to loosen. Their destiny is always to loosen. It is not to tighten.
Actually, that's a really good point. The universe wants to find rest and equilibrium, and you've got something under force and tension, and it's wanting to come apart, right? Yeah. Because that force is wanting it to come apart.
Yeah. This is entropy. This is basically disorder. And so the destiny of a screw is to loosen. And After a screw loses about 50% of its preload, it will absolutely loosen. So once this force over time diminishes,
So longevity is a fight against entropy.
yes, yeah, because
Wow.
there's lots of uncontrolled events that are occurring in a mouth. Like patients' mouths are fatigue machines. And so over time, uh, the things are going to happen where the screw is going to kind of slowly lose this preload, this store potential energy to keep the prosthesis from moving around, and it's going to get looser and looser over time. So really the goal here is, think about this as decay, right? I mean, it's a decay. It starts at a point and it starts to get looser and looser and decays. So with full arch prosthetics, like, we need to think that it's a complex mechanical system that's exposed to very complex forces. And so we need to maintain stability for a certain amount of time. Our goal is to basically to create a screw that maintains clamping force for as long as possible. And then in that maintenance cycle, you retorque the screw and or replace the screw and gain stability
Yeah.
back again.
I was just going to ask, so for patient recall,
Yes,
how many years go by when you want to like check the torque of their screws
I do it annually.
and you're getting out your torque wrench and checking all of them,
Yes,
and you might replace a screw.
I do. And I record, basically, I'm looking for how are we doing as far as maintaining, because every patient's different. And so I kind of collect data on, like, okay, well, are we torqued to spec? Are we torqued to whatever this specification is that I've determined?
All right, this is now anecdotal, but I'm
Right.
curious. With your 1 year recalls, how often are you retorquing of any significance?
So I typically find it depends. On some patients, they're all, everything's fine, you know, and then others, I will say, well, yeah, we're a little off. So I'll get them back up to like 15 Newton centimeters.
When okay, a little off is what? 5, 10 Newton
I get
centimeters?
rotation, yeah. So like, I'm looking for, okay, when does the screw start to rotate? And if it's and then I just measures, like, yeah, okay, I had to, that screw had to be retorqued. Now, what could have happened? It could have unwound or it could have stretched, and I don't know. Like
Oh, that's right.
on a cantilever situation, did the screw deform or did it unwind?
So
And
at what point would you say then I should just replace this screw?
yeah, I think I typically do 2 strikes. So if I have to tighten a screw twice, on the third time, it is out.
And this is a good note for, doctors getting into full arch dentistry, that the patient recall is important, and that the idea of setting them on their way, never seeing them again, or seeing them in a 5 year checkup, would you say that's just a bad idea?
Yeah, yeah. I,
Yeah.
I don't necessarily take it off, but I will validate the torque, because that's where you get, once you lose preload, right, and things start getting loose. What you get is, you get motion, micro motion
Yep.
in the system. You get wear and you get damage to the screw. So that's why preload is very, very important, and a fundamental to the mechanics of these prostheses.
Yeah, that micro motion, isn't that going to change the way forces are distributed? And it's going to, instead of distributing around the whole arch, it might start concentrating forces in a smaller area to cause a fracture.
It could, but more of what it does is, it basically accelerates the fatigue of the
Mm.
system. Essentially, fatigue is an enemy. So it fatigue, what it does is, you get small crack initiations in the screws, and then you get propagation. So when you fatigue something, you lower its ultimate strength. And so things break at much lower forces, when you throw cyclic loading and fatigue into it. And it has to do with these very small fractures beginning and then slowly propagating over time. And so it takes less smaller forces to fracture something.
So 1 year recall, checking screw torque is a must for prosthetic longevity for all
Yes.
NX cases.
And yes, and maintaining preload, like maintaining that clamping force to maintain stability.
And that preload clamping force, as you say, that's just measuring the Newton centimeter. That's the torque value of the screw itself.
That's our best guess as to what's happening.
You're right, because you might not actually know.
You might not know. And
because if you had a seating geometry that wasn't milled out right, you're going to get a false positive of torque.
Or a false negative. Yeah. I mean, basically, you could get a false positive because what you could be, because one is the friction is different. If you have a poor seating screw, you don't know what that friction is. So you might be stretching the screw way more than if you're just touching on a few little areas, there's less friction so you're cranking on that screw and you might be going to 15 Newton centimeters. You could be overstretching or putting too much preload on the screw, and then that's going to cause it. And then also the stress increases dramatically on those very small touch points. And that's why the Badger screw is kind of designed to have very nice continuous curve. And it's also designed to have a very specific seat.
Well, let's talk about that. So then that continuous curve and that specific seat was designed to solve what?
So one is it's to generate consistent clamping force and high clamping force. So we start off in zirconia very high. And the goal is to get us to those annual cycles. So as preload starts to diminish, we're still maintaining stability of the prosthesis as over time. And so the goal with the Badger screw is to maintain very high clamping force for as long as possible.
So the blue bar is initial force, the orange bar is what?
Settling force. So every screw. So as you basically tighten a screw and get it to its certain, you measure 15 Newton centimeters, right? You are there is, again, entropy plays a role here. So that initial stress is like a bunch of people crowding into an elevator, right? Initially you're all crunched up and then slowly you kind of relax. And so everybody kind of like relaxes. Well, at least I do. I don't know. but it's like that initial kind of stress when you get everything tight, and then what's going to happen is things are kind of going to settle out. So there might be a burr, or there's a little bit of deformation in the titanium in the threads. There's going to be a little bit of deformation in the screw seat, and things are just going to kind of relax. So that decrease in clamping force that you see is basically the stress relaxation in the screw shank and in the entire system.
Okay.
So basically of the main, the big screws that we've tested for direct to MUA, ours achieves the highest clamping force. And the goal, like I said, again, is to start high and maintain that for as long as possible.
I still don't fully understand how your geometry achieves the higher clamping force. What about your geometry, this concave geometry, helps achieve a higher clamping force?
It has to do with the amount of friction it has everything to do with how the amount of friction that we're putting on that the screw and the zirconia are having with each other.
The surface area that's applying friction is a larger surface area than other screws. Is that the idea?
It's also the direction of the force. So if you look at the shape, it's it's progressive. So whereas like a flat screw, this is an example of the like when you lose preload, right? When you stress a material, then it's you go from on to off really quickly. So with flat screws, basically the force is normal. The frictional force is always normal to the surface, and our geometry is kind of continuously curved, and so it's outward, and we're able to basically transfer. I think like how it achieves the highest clamping force is a good question, and it essentially it has everything to do with how the let's see the how do I say this? Yeah, I think it's more related to yeah that it's it has to do with the frictional coefficient of zirconia, and then also the fact that we kind of ramp it up. So here it's in this case it's kind of a very uniform. It's very consistent in a flat screw, but with us, it kind of gradually increases out towards the outer edge. So it's kind of hard to describe about why that. I mean, that's a good question and hard to answer specifically as far as like why does that shape increase the clamping force? And it the answer is that it's a fairly low friction environment. So we're able to efficiently convert our like torque to clamping force. It's that's probably the better way to say that.
Yeah, I mean, I could see how a flat geometry makes sense when it's like, no torque, a little bit of torque, boom, you're there. Probably it accelerates to its final torque very quickly, like you said, like an on off switch.
Right.
To where do you have a video of your screw and the Badger screw
Um,
and how it
Not in
applies
this
force?
example. Technically, I can tell you it's about a half a turn. So it's like you can feel it snug and then wham. It's very similar to a flat screw in the way it feels. Whereas like a flat screw is more like a quarter turn. This one is more like a half a turn. So
Okay.
it's like a different feel. But the yeah the way to look at it on how it transfers that energy, the best way to think about it is that it's very efficient at transferring that rotational motion into that linear torque. So we're able to, at 15 Newton centimeters, we're able to very efficiently create that preload via the because of the friction. Sorry, I kind of like tripped up on that, but that's actually a pretty deep question.
Yeah, and I mean, I think it's fascinating. Looking at a flat seat, it's easier to see how it's an on-off
Yeah,
type of discussion. I was speaking to a doctor at a conference recently that uses nothing but flat seat screws, and he's seated thousands and thousands of them, and he's
right.
saying he's having fantastic success. Not to say flat seat isn't a great geometry, but you designed yours to have this concaveness to it so
Uh-huh.
that as you approach it's more of a, I'm maybe struggling with you mentally, like if the Badger screw were to loosen, could you say it would take longer to loosen? Is that maybe some of the idea there?
Yeah, because of how one is because of the magnitude of the preload of the clamping force. So we start high, and so basically it the goal is to maintain that high clamping force under these vibrational like forces.
What about this as a potential observation? The distance that a screw would have to go to become loose is shorter. That distance is narrower, shallower, shorter on a flat seat versus a Badger screw. The distance would be slightly longer, right? So the amount of rotation to lose torque is a little bit greater than the amount of rotation to lose torque
Yeah.
in other screws. Is
Yeah,
that
because of its progressive contact, right? It's not as on off as like a flat screw. You know, it's kind of like it's still contacting during that compression. It's more nuanced than that, I think. But yeah, I mean that's the concept. The other thing too, though, really what inspired the shape is really about stress distribution. And so the fact that I'm really glad that we have very efficient transfer of torque to preload. That's a great that's a great benefit to the Badger screw. But the other benefit too is how it distributes stress into the material. So we control, like, in a very gradual way, um, on how you're going to stress the actual screw seat and material.
You walk me through what these diagrams mean, the upper one versus the lower one.
Yeah, so the upper one displays safety, factor of safety. So what's the kind of probability of having a fracture? And this is and then this is von Mises stresses. So this is basically finite element analysis. And this kind of shows where high stress concentrations are going to occur. And then this one basically gives us a model for what's the likelihood of fracture because due to high stress concentrations.
And the left versus the right image is showing what?
This is the Badger screw, and this shows where stress is distributed in the material. And then this is like a classic kind of flat screw that shows where that sharp corners and sharp areas are where stress naturally is going to concentrate because of the geometry itself.
Now, is there an argument that with a flat seat screw, you have compressive force on zirconia, and we know zirconia is very strong under compressive forces?
Yeah.
Any type of screw that's applying outward force on the prosthetic, could that cause outward stress to be concerned about?
This is compressive. These are primarily compressive forces.
Okay.
And so it's not, the wedge effect is different. It's not like a piece of wood and an axe. It's cylindrical. It's basically conical in shape. It's primarily compressive forces.
Okay.
That you're looking at it, and so the way that the stress is being distributed is much more evenly than it is with these. I'm not sure if I have it on my computer. I have it on my phone. But where cracks have initiated in 3D printed materials from flat seated screws. And basically the fractures start right in here, and then they kind of propagate out this way. And so these stresses are real.
So if an all-on-X arch breaks fractures at the screw channel, what are the potential causes of that? I'm sure there are many.
There are.
What could they be?
So I think the one that we see the most is where the occlusal part of the access hole is under tension, right? And that goes back to that model of, we have fractures here. Most of them occur, from what we found, and then here's one where it just began. I caught one. This is a baby crack that is beginning, and it hasn't fully propagated down through the prosthesis. And this one, I believe this was on a tie base with a fairly large access hole.
And is that zirconia or PMMA?
That's PMMA.
And that's really thick. Like it's not under designed.
No.
What happened? What's your diagnosis of this?
This has to do with a cantilever.
Cantilever was too long.
Yeah. And the only way we would and it's totally obeys like a lot of the rules of thumb. Like it's not out too far. But for him, for that patient, it is too far. And in fact, I went and did the finite element analysis on this, and the the solution, I thickened it, I did all kinds of stuff, and the best solution was the only solution was to actually cut it off, and essentially to minimize the amount of cantilever given the forces that patient could put on the
Was
prosthesis.
there
No, no,
was this
he had a failed implant posterior to that.
got it? So we were trying to get an all-on-3 to work.
Yes, I think that. No, I think maybe. Yeah, it might have been three or four. Yeah, but
Okay,
at least on this side, he had a failed implant.
and that
And
was just
so
cantilever length and his bite force and
yeah,
all of that. And
so generally, what we're finding is that a lot of fractures are initial. I believe this might be zirconia. That might be PMMA. That's zirconia here, and so the idea is that I think a lot of the fractures are initiating right here at these high stress concentrations and propagating down. There are some that can also initiate at the screw seat. It depends on how accurately how accurately the screw seat is and where the stresses are.
so I want to ask a two-dimensional question related to fractures. So
Yeah.
question one would be, as a clinician, what do you need your lab to do to mitigate fractures? And then as a lab, what do you need your clinicians to do to mitigate fracture? Because this is a teamwork event
It is.
and both need to do their job. But what are the important things a clinician needs to do to mitigate fractures? And then what are the important things lab needs to do to mitigate fractures?
Well, there's really four components to this system, right? We've got records, we've got design, manufacturing, and then we got delivery, right? So those are the four key components that need to be parsed out as far as like how do you get success. And the records have to be you need accurate data in order for you to design properly. And then on the design side, you need a way to design your prosthetics so that they're set up for success. And so generally, like as a rule of thumb, what I do is I tend to, on the lingual side, I tend to smooth embrasure spaces. I also tend to reinforce screw channels. Definitely, smaller access holes are better. We know that. And then the other thing too that we're launching is Will It Break? And that is the first finite element analysis software for design, which allows you to pre-stress or stress test your designs before you put them into manufacturing. And so this allows you to identify areas that are likely to fail, are likely to break, and that's takes care on the design side. And on the manufacturing side, we have other solutions that we're working, some cool projects that we're working on as well. And that's to kind of like, okay, let's validate the manufacturing. And then on the delivery side, the clinician, when it's time to deliver, the clinician should check for distortion and accuracy. And there's the Sheffield test, like the one screw test. It's very difficult clinically to validate that everything is good. But what I do is I put one screw in, and I use a Badger screw because of its centering. Right? There's no way for me to laterally create a misfit left
Hmm.
or right. It centers the prosthesis right on the MUA. And then I look for distortions in the manufacturing or in the data. So I want to see bullseyes on all of those screw channels first, because then I know if I don't see bullseyes, then I know that I'm going to put some additional stress on the prosthesis when I clamp it down. And so
Yeah, Curious question on this. So you're seating a prosthetic, you don't see bullseyes, and this is after osseointegration. So we're 3 to 6 months in, and the implants are stable. What happens to the implants or the prosthetic if you're applying force because the screw channels are
There's
off,
misfit.
but you torque it any? Let's say you torque it anyway.
Yep.
What is it just gonna like orthodontically move that implant? Like what happens?
Doesn't appear that the implants actually like after integration, it doesn't appear that implants move in any significant way. The stress gets dissipated in the entire system. So the prosthesis now has extra stress. So let's say a prosthesis is perfectly passive. Now it has to battle against the forces of chewing, right? And so it has to fight that fight. And the screws also have to clamp down and maintain and make sure that the prosthesis doesn't move. But when you have a non-passive prosthesis and you clamp it down, now you've added stress into the system. And so it has to fight that and the normal forces that it's exposed to. So your risk of fracture goes up. So what happens to zirconia is within a few days pop, or right at the time of delivery it pops because it can't because it can't handle the stress that you've put it in.
Yeah, before like photogrammetry and before some of these iOS systems that are close to photogrammetry, I gotta believe this was probably a big culprit in, full arch dentistry when, we're dealing with analog processes and stone models. And if
Yep.
you were slightly off, you're adding more stress to the system when you fully seat it.
Absolutely. I mean and that takes a toll on how accurately the screw is, when you have vertical or horizontal or angular misfits, like that all plays a part in like in the security and maintenance of that clamping force. And so if you don't have even distribution, if it's not passive, that's where you're going to get fatigue and screw breakage and loosening and fractures.
So yeah, accurate, super accurate records, i.e., photogrammetry. Or
Yep.
do you use photogrammetry, or do you use any other system to achieve your accurate implant positions?
I use photogrammetry. So I'm a ICAM user for 4 or 5 years now.
Well, as a mathematician and a physicist, I'm sure you were pretty sold on the ICAM when it first came out.
Yeah, I was. I don't know if I was an early adopter. I have the ICAM 3. So when that model was released, then I felt pretty confident that I can move forward. I do like that system quite a bit because I know I have to calibrate it every time, and these are very sensitive optical instruments, right? And so even changes in temperature and things like that can affect the small expansion and contraction, things like that. All that stuff needs to be. I like the fact that I have to calibrate it every time. I think that's important. And I have anecdotally I've found I've had it really was a game changer for me. Because I do things totally different than what I did in residency. I have the same principles, but I just apply them. I just use technologies to apply those principles.
My guess would be after using ICAM, your passive seating dramatically increased.
Absolutely. Completely changed the I mean that's why we see so much more full arch in the market and having available is because of technology advances in technology that have occurred, because we now can take a lot more accurate data. I'm not saying that it can't be done. With a highly skilled clinician can take really good impressions on a consistent level and get 20 micron ish results. But
Well,
that's a hard ask.
back we had a lab back in 2006. I remember we did a lot of work with Noble Biocare, and I learned about the in-mouth verification jig, right? And that to me made a lot of sense because you're verifying the implant positions cross arch with the jig, and you get it all together with like a light cured composite, and so that then becomes your master positioning guide. And yes, it's all analog, but it makes great sense how, all right, now that the implants are in and everything's integrated, we're going to do a verification jig, and then we'll build off of that in our
Yes.
master cast.
Yep.
Yeah.
And that's completely what I used to do. And now, now I don't even, my provisionals and prototypes are the verification jig, you know,
For sure.
and it's amazing how consistent it is.
And my guess is you're doing model free.
Yes.
Yeah. I mean, why have a model? A 3D printed model could add error to the system greater than what photogrammetry
Oh,
would give you.
definitely with 3D printed models. Yeah. I'm curious to see how this progresses. I think model printing is getting more and more accurate, and it will get more accurate, but at the same time, at the precision or at the accuracy that we're really looking for, I don't believe it's there yet.
So you pulled up this image, and
Yeah.
this is something showing like some stress tests.
Yeah, this kind of goes into like, basically what happens fundamentally when we take a regular bar, right? And here are some of the equations that describe the mechanics of a bar. And this is a very, very simple,
Oh man,
right?
not many people know what these mean, but you do.
Yeah, and this is a very, very simple geometry, simple structure, right? But we're we're Michelangelo's, right? We're creating. You take a simple bar and apply a force to it, and this is kind of the stresses that you'll experience. But when you have Michelangelo chip away and create these beautiful, create teeth, the stresses go up dramatically.
Yeah, tell us. What's the comparison here?
This bar, the bars are loaded with the same force. It's just that this one has some teeth put in it. And what this shows is basically that the stress, it has more to do with, instead of removing material, has more to do with the complex shapes, because the tensor field that's generated that mathematically describes how stress is going to be manifested in this.
Hold on.
In this,
I got to pause you and ask you, what is a tensor field?
it is basically a very complex. So we have different field theories in physics, like let's say temperature. Like I'm in a cold room and there's a heater over there. There's a scalar field, which describes like a cold area and then a hot area. So it's just a number in space. And vector fields are like electric fields, gravitational fields, things like that, but that give you a magnitude and a direction of like, I'm like very close to an electron or very close to a battery or something like that, and I'm going to feel an electric force if I'm charged. Then a tensor field has a lot more information stored in it, and it's basically talks about the where the stress is, the direction, and how the other elements that are in this field are related to each other. So it's more complicated than like vector fields. So the way we describe stress, and this goes into the finite element theory, is it describes the stress in relation to other small little elements in a structure. So we can take a structure and we can parse it up into small little packets, and then apply a fairly simple equation like Hooke's law or something that describes how, if one of them pushes on the other, how that's going to deform it. Finite element. So computers are really good at that. So we can break this structure up into little teeny chunks. Let's see if I can zoom in. And we see it in our meshes, right? So we can break this up into small little tetrahedrons, and we can apply a load onto this structure, and then the computers can calculate all the physics that's going on to each one of those little elements, and it can show, and it can give us an insight into where these like high stress areas are going to be. And that's fundamentally what finite element analysis does. And so it's used in aerospace and in, yeah, I mean, it's used throughout engineering to figure out, like, okay, we're going to make an engine mount bracket. We probably ought to figure out, what kind of forces and stresses it's going to be under, and in the design process.
Yeah, because it's all, you don't want to over engineer and make the engine mount bracket super heavy and super bulky.
Right.
So you want something like, mission appropriate, right?
Yes.
When you do it, when you engineer things, right? Like make it strong enough
Yeah.
and maybe a little bit stronger than it needs to be
Yeah.
to absorb high stress. But yeah, right. It's a, value engineering or, mission appropriate engineering. I'm noticing here on this heat map that we've got a lot of force in the interproximal areas.
Yeah.
And you would mention that a screw channel in that area is like kind of like I don't want to call it a kiss of death, but it's something that so if there's a screw channel in your interproximal areas, now what are you doing to sort of add?
Typically, we'll reinforce and smooth this area out. Like, let's say right here on the lingual.
You'll violate aesthetics.
Sometimes you have to. Yeah.
And this is a good point, right? Like,
right.
You are looking at a prosthetic through the lens of aesthetics and engineering. And if the implant's placed where it is and it's right between two bicuspids, okay, Susie, yeah, right here on the lingual, we're going to have a little bulk, but let me tell you why that's appropriate.
Yeah.
So yeah, it'll look less than ideal aesthetic looking, but it's going to last. And my guess is as soon as you tell the patient that, they're like, perfect.
Yeah.
Right?
And I think this is the kind of where we need to go in our industry, because we need, these are engineered products. These are engineered individual one-off pieces that are going into a mouth. And I think we really need to up our engineering game, because that's what they are. And so they're designed to mimic tissue, but they're also should be designed to mechanically last and to function, because that's what the patients are wanting. That's what they're paying for, is something that's going to be stable. And I think we've neglected the complexity, how mechanically complex these prostheses really are. And I think the goal is to kind of improve. That's the long-term goal, is to improve this process and make it better, because fractures are I think a hidden cost that we don't really address very much. We just kind of sweep it under the rug, and they're a big inefficiency in our clinics and in our industry, in the manufacturing side.
Yeah, as being involved in material development, a lot of labs or doctors will ask, well, how strong is your zirconia?
Right.
And that's a valid question for sure. But is it like, well, it's strong enough to last as long as you take good records, have a good design, do good manufacturing, and you deliver it right, right? So like when someone sends you a picture and says your zirconia broke, man, there was a lot to investigate to determine a root cause, because we don't know just by
absolutely. It's easy to jump on like a one thing, but it's like vastly complex. So lots of little miracles had to occur in order to have good success.
And after talking about all this, my good friend Austin Heath is a big advocate for the I-bar, this titanium substructure.
Love that guy.
And the zirconia superstructure.
Yeah.
Obviously, a lot more complexity, a lot more milling time. You have two parts you're assembling.
Yeah.
But man, the more I talk about this with people like you, it's like, man, that titanium bar really is kind of like this warm and fuzzy blanket that can, eliminate a lot of error or stresses entered into the system versus a monolithic full arch zirconia. What's your reaction to that? And do you like doing the titanium substructures or not?
Yeah, I do them. So it depends on it's totally individual based. I do not believe that you can or should or always do one application. Like I don't think everything should be a titanium bar. I think some scenarios they should. Um, and there's some downsides with titanium bars too, because you're basically adding complexity to it, and we don't necessarily know if that is the we don't know the answer to that, if that's the bulletproof way. Like that this will survive anything, because zirconia and titanium are very different. And so when you apply a load to them, one is going to flex and one's not. And so it doesn't mean that you're completely failure free. I do think there's some advantage to it, but we're going to be actively testing that. And titanium collects plaque. It does. I mean, plaque sticks to it. Even you do have to, if you highly polish titanium, it performs pretty well. But highly polished zirconia, there's no question about biology there. Like that, it just doesn't retain as much biofilm. And so that's I think there's kind of arguments this way and that way. Is it the ultimate solution? I don't think anybody knows the answer to that yet. So I would say, depending on the scenario, it may be the right solution. Some pterygoid cases, some cantilever cases, I design bars, but I've also had fractures and failures in bars too. So
With titanium bars fracturing?
yeah, veneering zirconia.
Oh, like the zirconia crowns coming off?
Yeah, the wrapped zirconia will get a fracture.
Oh, because it's now thinner.
Yep. And so it's not, in some scenarios where you have the space for it and things like that, I think it can work well. It definitely can. And so I don't believe that it's always. I think it's more nuanced than that.
Well, given I'm not a screw expert, but I've had a few conversations, and this is my third one on prosthetic screws in like the past month. I feel like if I was going to go in for an all-on-4,
Yeah.
I would want a titanium bar specifically for the reason of understanding that screw force to titanium is going to, tell me if I'm wrong here, if there's a little bit of torque or if things are slightly off, titanium will absorb that stress better than zirconia will. And now your zirconia arch that's being cemented to the titanium frame underneath, that's just only absorbing chewing force. Is that correct? Tell me if I'm wrong.
No, the whole thing is they're all tied together. And so yeah.
It's not that simple, Rob.
Yeah. They're all tied together. And so we're working on understanding the stresses on these more complex assemblies. I don't have the answer to that quite yet, but I will.
Let's talk about will it break. Let's
Yeah.
talk about that briefly, because I want to do a whole nother episode on will it break.
Yeah,
But
yeah.
when you say I don't have the answer to that yet, I think I know why, is because you plan to test it in your software.
Yeah. Yeah. I mean, we're actively working on complex assemblies, and it is much more difficult to, we have to model cement, we have to model all these different material, and we have to get good data. Like, how strong is your zirconia? Like, what does that even mean? Like when they.
And it's stronger at the base when there's less
I know.
yttria
Yeah.
than the incisals. So there's like a strength gradient through the
I know.
object through the puck, and then where was the arch oriented in the puck?
Yeah.
Man, that's got to be a really difficult job.
Yeah. I'm that is we won't be touching that for a little while because that is I think that's a really difficult problem. But
So many variables to try to
yeah, what
control,
I'm
right?
using now is I'm just using straight 4Y for most of my arches.
So solid white, and then you stain or micro layer porcelain.
Yeah, we micro layer and we usually do we'll get stained like like an A1 or something, but we a lot of times we won't I I even quit using multi-layer. Like so there's gradients, there's multi-gradient and multi-layer, and then there's you know and then there's just straight up like monolithic 4Y or 3Y, and then there's pre-stained. So we'll use pre-stained monolithic.
So you like all of the yttria being the same just for a variable control?
Yeah, yeah,
That doesn't surprise me,
yeah,
Mr. Mathematician.
yeah. I mean, you've got to, I'm looking for some uniformity here, and that's going to be easier to validate, right? And so
Yeah.
we're also mechanically testing, independently testing materials, so that we can really truly understand what these materials are doing. Because like, look at the 3D printed resins, like they don't give you any information about like what it actually is. I think Rodin is pretty good at publishing their data, but
Mm.
like the resins, it's just all over the place. It's like,
Yeah.
you know, it's it's
It's dentistry.
yeah, totally. It's not very useful for engineers. Let's just say that what's being published is not very useful.
So that you're doing all your own engineering so that you can have a clear understanding with the way you think.
Right.
So give me an infomercial on will it break? And,
Yeah, I don't have a lot on this slide deck, but Will It Break is basically like I said, it's a finite element software where we've automated a ton of features on it. So basically, you just submit your saved and merged designs, and you upload your construction info file. And what we do is we stress it and then tell you where there are hotspots where we apply like a failure theory to it, and we tell you basically these are some hotspots or areas where you should be you should be concerned about.
let me, let me,
Yeah, it's in beta testing right now, so it's not fully the rewrite that we're doing right now is a more sophisticated model.
but fundamentally, it's you load a geometry
Yep.
and then how does it know in which direction to apply the occlusal forces? It's just, articulating a bite and then just going through an average condyle
Yeah, so it,
placement.
it basically puts a load on like you enter in your patient's bite force, and basically you can use literature norms, or we have like beast mode. You can put like 1,000 newtons on it, and just
Sasquatch mode.
yeah, exactly. So you can basically it just puts an MIP kind of like MI load on it. And then we also stress it for cantilevers, like an olive pit. We'll apply a load on the distalmost teeth. And then also we have a anterior, like an incising, like beef jerky or fishing line or something like that.
How
So we'll
about
put a
that?
load. Yeah.
They, you're from Montana. Beef jerky or fishing line are
Yeah,
both in the same day.
that's
I love
right.
it.
But that's
Awesome.
the
So
yeah, so that's the goal. That's basically right now that's kind of how the software is set. So we kind of automate all of that stuff plus our all the back end kind of like modeling. So it does a lot of complex math, and then it spits out a heat map and tells you like red is kind of bad,
yeah, so as a designer or a lab,
right?
this would be a great CYA to make sure you
Yeah,
are designing the prosthetic properly. And as a doctor, this might be something you demand a lab to perform.
Yeah.
just so that it's this sort of, sanity check before
Yeah.
we proceed with manufacturing.
Yeah, and for your design teams, I run a lab too, right? I mean, I have a lab, and so for your design teams, it's really good for like training, like like hey, let's run some designs through. Here's how, like these are some areas that I want you to watch out for.
Well, and let's take the olive pit, right? If we have an older, stronger male with a stronger bite force, and the doctor asked for a full 15 millimeter cantilever as a lab, you run
Right.
it through this test, and then now you're having a data-driven conversation with, "Hey, doc, we should not,
Yeah.
look at the heat map. We should shorten the cantilever." Well, the doctor and the patient both emotionally probably don't want that. However, it's, if the doctor were to send this to the patient, like, "Hey, man, if you're not going to get that extra molar we were talking
Right.
about, here's a heat map. If you want a long-term warranty with this thing, we're going to have to shorten it." And it's a data-driven discussion now.
Yeah, and the conversation is always the question in engineering is always quantify. How do let's get away from qualifying information to quantifying it. And so that's where you want to steer the conversation. And I've used this clinically as well. Like Mrs. Jones, you see that second molar? Like I know you want a second molar back here, but this is why you can't have it. Clinical application as well. I think hand in hand with our partners, our clinicians and technicians, it helps us make better decisions. I mean, that's the goal is, like I said, the four pillars of success,
Mm.
is records, design, manufacturing, and delivery. And when we tie all those together, that's really that's how you get success.
I love it. Well, I think we should end on that. When could we do another recording for the Will It Break software? When do you think that's ready for prime time and doing a deep dive into that?
I think we should probably are we are actually getting automation should be really up and running by the summer,
Okay.
like with more complex things. And I think our coders are working, they're working really hard right now, and I think that will be kind of the new model is going to be kind of a game changer, I believe. So it's that should be up and running probably midsummer, we think.
Awesome.
Yeah.
Like in the fall.
Yeah.
All right.
We have a lot of labs that are really they get it. They totally get it. It's
But yeah,
I mean we need this stuff.
any lab doing a lot of full arch, you want this to keep your designers accountable, but also have that informed discussion with your doctor to say,
Right.
"Hey, we can't, we're going to have to bulk in it here. Here's why. Tough luck unless you want to sign off that you're going to pay 100% for a remake."
Yeah.
You know?
Yeah. I mean, yeah, exactly. It has a it 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 it's a good conversation starter on how to solve some of these challenges, like
Yeah.
between the lab and the clinician. It's like real numbers about like on the design side.
Well, Dr. Sven Bone, this has been super fun. We probably could have talked longer, but I feel like we covered a lot of ground.
Yeah.
Thank you so much. People can find the Badger Screw on your website, Smart
Yeah.
Mouth Technologies.
Yeah. Go to store or home. Yeah.
Here we go. It's right here.
Yeah. We've got,
So it's
and the starter pack is ending June 1st. So it's coming up. So we've got some pretty good deals on the Badger Screw. It's truly, there's a lot of engineering that's gone in behind it.
so it's a 10 pack of screws and 4 drivers, different lengths, and one for angled and one for straight.
Right.
That's pretty good.
Yeah, man. And our ExoCAD libraries are free to download as well as our milling strategies. And they are, it's a great. We've had a lot of people with success.
Awesome.
Yeah.
Well, thank you so much,
Thank you,
Dr.
Matt.
Sven.
Yeah,
We'll see you next time.
absolutely. We'll do it again.